billion years ago, it is thought that all matter and energy was at a point. And by point, I mean about 200 miles in diameter. But relative to the size of the known universe now, that is an incredibly small point of infinitesimally high matter and energy concentration. And it blew up, and it's been expanding ever since. Now, a popular misconception about the Big Bang theory is that there was a bang and it's over. That's not the case. If you ever think about seeing an explosion on TV, a car explodes or something like that, it's all bang. We are living inside of an ongoing explosion. This is an explosion that is going on, and we are inside of it. I'll show you where we are relative to the rest of the universe. So again, all matter and energy was at a point, blew up, it's been expanding ever since. The theory that was held for a long time is it's just going to keep expanding forever. It had overcome long ago its gravitational maximum. It's just going to keep on expanding. Things are going to get less and less concentrated, and then just keep getting bigger and bigger. Recently, and by recently I mean the last 25, 30 years, astronomers, astrophysicists, other people have discovered a lot of matter in the universe that we didn't heretofore think existed. It didn't emit light, black holes, and then also dark stars, quarks, all sorts of things that are beyond the scope of this class. The point is that there's a lot of matter here that we didn't realize existed. And so it may be that we have not, in fact, surpassed our gravitational maximum. The significance of that is that maybe that the universe gets to a point where gravity causes it to stop expanding, like stretching a rubber band, and then it starts to shrink back onto itself. Geologists affectionately refer to this as the big crunch. So it may be that we come to a point, this maximum, and come back down, crunch back down onto ourselves to that same point, and then expand again. I read an article maybe 3 years ago in Physics Today that said, it's very difficult to understand, mostly math, but it said that not only is this going to happen, but it's happened 6 or 7 times in the past. There's been this yo-yoing of an explosion that comes back down onto itself. Obviously a very poorly understood phenomenon, but this is the scientific explanation of what has happened. We know that the universe is expanding because something called red shift is going on. Red shift is when you look at stars, distant stars, through a telescope, the light that's emanating from those stars is shifted towards the red end of the spectrum, the electromagnetic spectrum, visible light. Maybe you don't have an intuitive feel for that, but it is very similar to what happens with sound. And if you're standing on Commonwealth Ave and a motorcycle is far off in the distance and it's coming towards you, what do you hear? Yeah, so the pitch, so if it is absolutely high and fast. If you're standing here and it's coming towards you, you hear it sounding low and then come up to high and fast, right? So it'll go when it gets to you, and then what does it sound like when it's going away from you? Right? If you're on the back of that motorcycle, if you're driving that motorcycle, is that what you hear? Do you hear this cyclical thing? No, you hear the same the whole time, right? So sound is shifted by the Doppler effect as something is coming towards you, and then as it's going away from you. So the going away Doppler effect analogy is red shift. We will know that the universe is starting to contract onto itself when light from distant stars, instead of shifting towards the red end of the spectrum, will be shifted towards the blue end of the spectrum. We know, okay, it's starting to contract again. How worried should we be about this? Should we be worried? Oh gosh, the universe is going to collapse? Yeah, we shouldn't be worried at all, exactly. It's been 15 billion years and it's still expanding. So, worst case scenario, it's going to be 20 billion years if it starts going back 5 billion years from now to a big crunch. Nothing we need to worry about. But this is what the current understanding of the whole universe is. And we've recently photographed the edge of the universe. Quite spectacular that we're able to do that. Again, put these all out. Okay. So dropping down a level to the galaxy. There are many known galaxies in the universe. Again, this is not a class on cosmos, so we won't talk about them. But we are in a galaxy called the Milky Way Galaxy. The Milky Way Galaxy consists of between 200 billion and 400 billion stars. Unfathomable amount of stars. And most of them are in this central bulge. So I've tipped this up in this cartoon diagram. If you looked at it flat, you'd see this central bulge where most of the matter and energy are located. And then there are two arms, and the arms are slowly rotating. The whole thing is slowly rotating due to conservation of angular momentum. So those multiple arms there are not the case. It's just designed to show movement. So there are two arms, flattened disk, slowly rotating around, 100,000 light years across, again, 200 billion to 400 billion other stars in addition to ours. It's slowly moving around, and I put that you are here because we're about 3/5 of the way out one of the arms as the matter trails off into nothingness, into space. So we're just sort of, in many ways, an insignificant little planet circling around an insignificant little star as the matter from the Milky Way Galaxy trails off. If you've ever seen pictures of the Milky Way Galaxy, we're able to photograph it even though we're inside of it because we're at the sort of edge of it. We can look into it that way. So that is the galaxy dropping down a level. Dropping down one more level, we'll look at the origin of our current solar system. And we do this again. I will talk about this stuff when we talk about meteorite impacts. So conceptually, this isn't a picture of it, we used to be a first-generation star and solar system. Pretty boring, probably mostly hydrogen and helium is the thinking. The sun at the center of our first-generation solar system burned out and exploded and engulfed the other planets, or the planets of it, and caused something called a nebular cloud to be formed, which is just a big accumulation of dust and gases. Gravity, something that we'll look at either the end of today or on Wednesday, gravity, the force of attraction between two particles, caused two things to happen. Caused the dust to start to accrete together, to slam together. Two particles of dust exerted gravity on each other and came together. And then two more and came together. So this planetary accretion is what it's called, caused the cloud of dust and gases to start having larger chunks in it. The sun, as well as the planets that are orbiting around the sun, Earth, for example, used to be the size of a speck of dust. And then dust kept accumulating onto it, larger and larger impacts, caused the Earth to grow to the size of a golf ball, and then a baseball, and a softball, and a basketball, going bigger and bigger until it became the size that it is today. So that's planetary accretion. All of the planets became larger and larger with the sun in the center. And so that's what this picture is. The first generation star burned out, exploded, and then the accretion, the condensation of the material caused it to start to flatten and spin. Again, I always struggle with how far to go into this in a non-science class about conservation of angular momentum, this rate of spin. But so it caused it to flatten and start spinning in one plane. So going from A down to here, these are called planetesimals or protoplanets. Planets are starting to get larger and larger. Asteroids are hitting them, growing bigger and bigger. At the same time as the rocks were getting together, essentially, the nuclear reactions were happening that caused just simple hydrogen and helium and simple elements to fuse together, the process of nuclear fusion, to make the more exciting elements in our solar system. All the naturally occurring elements in the periodic table happened during this transition from a first to second generation star. Atoms slamming together, making the fascinating stuff that's on Earth that we'll talk about for the rest of the semester, and the other planets. So we have these planetesimals, the end of A goes up to the beginning of B, the spinning, flattening, and growing the planets to the size they are today. So we are now orbiting around a second generation star. So then we get to where we are now, really, our solar system. And we already talked about all of this. The second generation star. We have how many planets? How many planets? 8, right? We kicked Pluto out. Why did we kick Pluto out? Dwarf planet, right? So Pluto, it has a weird orbit, but also in order for something to be classified as a planet, it has to, they call it, clear its own neighborhood. It has to be big enough and exert enough gravity so that any rocks, any sort of debris in its area will accrete onto it. And that didn't happen. News for maybe some of you, maybe not. We should have 9 planets, and I'm not talking about Pluto. I'm talking about the fact that on the other side of Mars, there is an asteroid belt. Lots and lots of asteroids. Why am I not quantifying them? Well, it depends on when you cut off the size. If you talk about really, really small, you're talking about trillions of asteroids. Big ones, hundreds of thousands, and they are on the other side of Mars. It was a failed planet. There should be a planet there, but it didn't get its act together in the process of planetary accretion. So we have all these asteroids that are on the other side of Mars. How worried about that should we be? Hundreds of thousands of potentially life-compromising, if not ending, asteroids on the other side of the next planet. Should we be concerned? This class on disasters, we're going to talk about them. Anyone concerned? No, why not? What? Oh, but it has happened. It's happened a lot. It's happened a lot. We are overdue, my friend. So yeah, it has happened. It has caused almost game-ending extinctions. But it's a good point. Or a good guess. The reason we shouldn't be worried is because they're tracing within our equatorial plane. So this Earth is going around the sun. They're doing the same thing we are doing. They're not coming from above. They're not coming from below like comets are. And unless something knocks them out of their orbit, they're just doing the same thing we do. So they're harmlessly on the other side of Mars. But that should have been a planet. So the first 4 planets, as you may know, this is on the next slide, are the rocky planets, right? The terrestrial planet, Mercury, Venus, Earth, and Mars. Rocky inner planets. And then the outer planets are the Jovian planets, the gas giants, Jupiter, Saturn, Uranus, Neptune. Big accumulations of gas, essentially. So we will look at what happens when a comet, not an asteroid, hits some of the big planets. We'll talk about comet Shoemaker-Levy and what happened with that. So now we drop down to Earth, where we'll stay for most of the rest of the the semester. We'll go back to space for meteorite impacts. In several ways, this is an average terrestrial planet, although obviously from the point of view of life and free water, it's quite a spectacular planet in our solar system. But it's average in several ways. So that's a terrestrial planet, again, where the Jovian planets are the gas giants, the outer part of the solar system. The things that make our planet spectacular and filled with disasters are first that we have free water. Free water just means liquid water. People that study the possibility of extraterrestrial life, they disagree on many things. One thing they all agree on, that is to have extraterrestrial carbon-based life forms, you need to have vast quantities of water. So it is thought that water, liquid water, is quite literally why we are here. You cannot have life unless you have vast quantities of water. Other planets have some to large quantities of water, but it's either in a frozen or in a vaporous phase. There's some evidence that Mars used to have liquid water, drainage patterns, etc. But right now, Earth is the only planet that has these vast quantities of water. It makes us incredibly notable and exceptional. We also have plate tectonics. We're not the only planet, but we have plate tectonics. That's what we're going to be talking about on Wednesday and Friday. Plate tectonics, the fact that inside of Earth is hot. We'll look at that in a minute. Outside of Earth is cool. So the cool stuff's moving inside, and the hot stuff's moving outside. And that makes for terrestrial land masses to be built, which is handy given that we're terrestrial beings. If it weren't for plate tectonics, the things that cause these horrible disasters, earthquakes, tsunami, volcanoes, all of the terrestrial land masses would be reduced to below sea level within a couple 100,000 years. Sounds like a long time to you, but it's nothing given the fact that Earth is 4.6 billion years old. So we need plate tectonics to have terrestrial environments. And then we have the 3 types of rocks that we talked about last time. So I'll kind of go through those briefly. Perhaps not the best titled slide, but this should be titled Planetary Differentiation. So make sure you understand that, and make sure you understand the difference between planetary differentiation and planetary accretion. So accretion was when the asteroids the meteorites slammed onto Earth, grew it to the size that it is today. That's planetary accretion. Accrete something, stick it onto something. When Earth was first more or less the size that it is today, it was a molten, homogeneous ball. Remember, from rocks and minerals, homogeneous. Same thing throughout, and it was liquid. Gravity caused that to happen, right? Gravity got larger and larger on Earth, caused more and more things to slam onto it. Once it grew to this size, gravity wasn't done with it yet. The center of Earth's gravity is in the center of Earth, and so gravity pulls most strongly on the densest materials. So we started looking at rocks and minerals last time. Gravity pulls the most strongly on the metals. So you can think of the center of our Earth, and this is a very rough coarse approximation, we'll fine-tune it later, as a solid metal ball, iron and nickel. It should be liquid because it's so hot, but the crushing weight of the overlying material that gravity's pulling causes such tremendous pressure that it's forced into a solid. So you have this solid metal ball in the inside of Earth. Some of the iron and nickels had complexed, or turned into these molecules, with silica. Silica is much lighter, as we'll see with volcanic material, than the metals. So it made this glassy metallic stuff, silica mixed with iron and nickel, get pulled as well, but pulled less strongly. And so that became the sort of middle part of Earth. Roughly, we're talking about the mantle. People talk about the mantle as being liquid and flowing. It's almost solid. There's nothing liquid about it. But it's just soft enough, just hot enough that it can very slowly flow. So that's the mantle. Iron and nickel that has complexed with silica. And then our crust. Obviously, this is a simplification given the rocks and minerals that we looked at. But our crust is essentially a thin silicate, thin glass shell. So you've heard about these, I'm sure, since very early in your education, the core, the mantle, the crust. But there are two other layers that happen in the process of planetary differentiation. Plate tectonics, which was very active in Earth's early history, was causing volcanoes to spew out huge quantities of gas. And this is a part of the layering process. These gases were still held here. They're not going off into space. They have mass. They're being held here by gravity, but they're so light that they're in vaporous phase at Earth's surface temperatures and pressures. So gravity is sorting, differentiate, to tell the difference between two things, right? Gravity is sorting out the heaviest to the lightest in these onion-like concentric layers. So that was the form of our first atmosphere, volcanic outgassing. We'll talk about that in many different places in this class. And I put this picture up because if you could be on the surface of Earth right as this was pretty much complete, but before life started being here, if you looked up in the sky on a beautiful day, instead of it being sky blue, it would be blood red. If you looked at the sun, instead of it being yellowish orange, it would be navy blue. That's because of the way these gases scattered light in Earth's early atmosphere. So then this layering became complete when lots of the water, which is heavy, H2O, started to cool. We're about midway through our cooling history on Earth. We're starting to cool from the outside in, rained down to the surface of Earth and became the hydrosphere, hydro water. So it became water mostly in the oceans, but then also rivers, lakes, streams, and groundwater. So liquid water coats the surface of Earth more or less. Then we have this last layer of atmosphere. And there's some, but by no means an all-encompassing list of gases. Now nitrogen is the biggest gas by percentage in our atmosphere. So we have these layers, again, from heaviest to lightest, from most dense to least dense. And that's the last part, that when Earth started cooling, a lot of that liquid water changed from a gas to a liquid. So those are the layers. Make sure you understand the difference between planetary accretion, growing, and planetary differentiation, sorting. So as we said, Earth is common in some ways with regards to the terrestrial land masses, but it's also quite unique. And I have a slide on each one of these, so no need to write them down. We looked at the rock cycle last time. We will look at the tectonic cycles for the next two classes. So then the hydrologic and biogeochemical cycles are also things we will look at in a general point of view from looking at disasters. We looked at rocks again last time. There are three types of rocks. We looked at the types of them. One thing that we didn't say is that these rocks are always changing into the other types of rocks or to a different version of itself because of tectonics and weathering. So you have this igneous material, it comes up, it cools slowly beneath the surface or quickly at the surface. Cooled lava or magma is igneous rock. As soon as it's exposed at the surface, remember it goes through the process of weathering and making sedimentary rocks, but you can squeeze and heat sedimentary rocks, turn them into metamorphic rocks. You can heat metamorphic rocks even more, turn them into liquid, which is not a rock, right? You can melt igneous rocks and make them into a different type of igneous rock. You can rework sedimentary rocks, make them into a different sedimentary rock. We can squeeze or heat a metamorphic rock, turn it into a different metamorphic rock. And I'm not trying to be confusing here. I'm just saying that these three rock types are always turning into the other two or to a different version of itself because of these cycles that are going on the surface of Earth. Tectonic, which we'll see, and then also the hydrologic cycle. 1.36 billion cubic kilometers of water cycling around on the surface of Earth. And it's kind of funny, most of the water is in the ocean. We'll look at percentages later. The smallest reservoirs here, 1/1000%, is in rivers. And rivers will do tremendous work on Earth and cause tremendous amounts of disasters. And we already talked a little bit about cyclones, right? Hurricanes, typhoons, cyclones. 1/1000% of the water's in the atmosphere as well. And you talk about these massive, massive monster storms. So you don't have to have a lot of water in these areas in order to do a lot of work, cause a lot of death and destruction. So we'll look at the hydrologic cycle when we look at rivers and flooding, as well as atmospheric natural disasters. Briefly, this sounds like a long, pedantic word, but biogeochemical cycles just means that you're tracking, it's implying there's a sort of bookkeeping that's able to be done. You're tracking an element as it goes from the life to the rocks, to the atmosphere. Wherever these elements go, you can track them and sort of make a diagram of what's going on. So these are some of the main biogeochemical cycles on Earth. We're not in this class, in the way that we did in Geoscience 1, concerning ourselves with the phosphorus, nitrogen, or oxygen cycle, but we are really caring about the carbon cycle from a climate change point of view, looking at how we're throwing this cycle off balance by digging up both coal, oil, natural gas, burning it, putting too much of it into the atmosphere, some would say, and volcanic eruptions putting these carbon elements into, or molecules into the atmosphere. So look at the carbon cycle. I'll skip over nitrogen. We won't be dealing with nitrogen or phosphorus, just to know that there are such things. And then the water cycle, which we already looked at. The last cycle here, the tectonic cycle. Again, this is just a real brief overview because we're going to spend 2 days on it. The inside of Earth is very hot. Outside of Earth, relatively speaking, is cold. So the cold stuff's diving inside, the warm stuff is coming out. And so you have this constant cycling that's creating new land masses and is also causing our first 3 natural disasters. The inside of Earth is hot. The reason why is threefold. 3 things that are going on, that cause inside of Earth to be hot. First one we already talked about, planetary accretion. Those meteorites streaking through the sky at 650,000 miles per hour, huge amounts of energy, right? Stopping instantly turns into heat energy. So every time something accreted to Earth, it caused heat. That's why Earth was a molten, homogeneous ball. Nothing could stay solid, it was too hot. And then also, in the transition from the first to the second generation solar system, we talked about fusion at the nuclear level. Some of those nuclear fusions made radioactive materials. So inside of Earth, we have radioactive materials that are undergoing alpha or gamma or beta decay, and radioactive decay is heat. So we have this kind of self-sustaining heat mechanism because there are radioactive materials inside Earth. The last part, gravitational energy. Again, the center of gravity is in the center of Earth. It's pulling on this stuff. We're not getting detectably smaller, but we have gotten smaller because gravity is pulling on Earth, and this pulling causes friction, which is heat. So those are the 3 reasons why the inside of Earth is hot. Because asteroids, because of radioactive material, and because gravity is causing friction. So just to end on